Coming up.
China docks and refuels a space station module.
Peggy Whitson sets a record.
I let Ben ask me silly questions.
All that and more. Stay tuned. Tomorrow begins right now.
Good morning. How's everything up in the sky?
Welcome to Tomorrow Space. I am Carrie Ann. This is Orbit 10.16. With me is Jared and a Mike. I've got a Dutta. I've got a Ben. I've got all kinds of fun things. Oh my goodness, this is going to be an amazing show. Thankfully, I'm also as purple as our open, so that's fantastic. Unfortunately, we had no launches this week, so what we're going to do at the top of the show, like we always do, is thank our Patreon members. I would like to start off with our Escape Velocity members. These are the people who have given us $10 or more for this particular segment of this particular episode, and as always, they get access to our Slack channel, which is the weird, wild world of Ben's mind. So only enter if you dare. If you would like to enter into the weirdness that is, you can head on over to patreon.com/TMRO. Oh my goodness. Boy. So, because we have no launches and that's kind of a sad thing, we're going to start off with some things that we really, really like, which is Pluto.
Yeah.
Because it's an awesome planet.
Yes. Even I will admit it now.
Yes!
It is an awesome planet.
I win!
So this is really cool. This is kind of just a little insight into what it's like to actually make a mission happen. Because we talked about Cassini last week and the long time it took Cassini to get to where it is now. Well, the next Pluto mission is already in the works. They actually held a workshop earlier this week in Texas to discuss what they're going to be doing for the next Pluto mission. So, as we all know, New Horizons flew by Pluto on July 14th, 2015, and it was an amazing mission. It gave us pictures like this of Pluto itself, which is just mind-boggling geology, all crammed together. It's like a smorgasbord of geology. It just doesn't make any sense. That's the amazing thing about it. So scientists, they routinely meet to plan missions, potentially 20 to 30 years out. It's like making a wish list of what you want to do. And it was very interesting because the group that met included Alan Stern, who's the principal investigator for New Horizons. They basically decided that the next mission they should send to Pluto should be an orbiter with a lander. So really, one of the biggest challenges is getting to Pluto fast enough. But you can't get to Pluto too fast, because if you want to orbit Pluto and you're moving very, very fast like New Horizons did, you're going to have to carry a huge amount of fuel in order to make that happen. So scientists have proposed using a RTG-powered ion propulsion system.
Okay,
so,
what is RTG?
I
was so with you.
Okay, radiothermal isotope generator.
Okay, that
good stuff.
Almost helped.
Yes.
Okay, but
a big nuclear battery.
Okay, that's fair. And ion propulsion is something that we've talked about a little bit about over the last couple of weeks, so I think I have a general idea of that.
Yeah, basically you just fling ions out the back end of your spacecraft. Not a lot of thrust, but you can keep it on for a very long amount of time.
Nice.
So the thing that they wanted, with the ion propulsion, they think they can get to Pluto within 3 to 4 years.
That's not bad.
And actually slow down in time to do that as well. So basically accelerate halfway out, decelerate halfway out. And it's just a very interesting idea. Now, they've also floated using the idea of fusion propulsion, which actually the type of fusion propulsion that they're talking about, directed fusion propulsion, is currently in a phase 1 study by NASA. So it's not necessarily like, we always joke about fusion being, 10 years out, 50 years ago.
Right.
It's kind of one of those things where they're really actually putting the effort into it. Now, the orbiter that they designed would stay there for 3 to 4 years, and they potentially want to include a lander to drop it to the surface of Pluto as well. So
kind of like what we've done with Mars, right? Like
yes,
that's the same concept but on Pluto. Yes.
Yes.
Yay!
This seems to sort of follow NASA's mission architecture when they're exploring something, which is basically you do a flyby first, then you put an orbiter in orbit around it, and then you put a lander on the surface. So really cool stuff that they're potentially going to be working on for the next 20 to 30 years with the Pluto mission like
And
that.
lander, not a rover. Is that correct?
Yes, just a stationary lander so that it can be in a certain area. And they want to use things like optical communications with lasers and other systems like that. It's just overall very cool mission architecture that's actually getting started right now. So awesome.
Nice. That's very, very cool.
Very interesting.
Yeah, that's really interesting.
Yeah.
I like it. Okay, I feel way better about not having launches. We'll have some next week. It'll be fine. So, Mike,
I should have some tomorrow, and that should be awesome.
that should be really awesome.
Can't talk about it.
I don't know anything about that.
Yeah.
Doesn't look like anything
Never
to me.
mind. Yeah, sorry.
Mike, tell me about some things we can talk about. What is going on from Canada? This is so confusing.
yeah. So this is it's kind of actually an old idea that's gotten new life. And what we're talking about is more launches potentially happening in Canada from Nova Scotia using Ukrainian rockets. And this is a really cool concept using some hardware that they have to create their Cyclone 4 rocket. And with this, they have actually been doing a deal with Brazil over the past 10 years to try to make this project happen in the Alcantara in Brazil, which is not far from French Guiana. But the project was canceled by Brazil and when they just pulled out of the project in 2015 for economic and quote-unquote political reasons. Now, this whole idea, though, of launching a Ukrainian rocket from foreign soil, since they've kind of lost their deal with Kazakhstan to launch some of their rockets that they build, like the Zenit rocket, from Kazakhstan. So there's a new company called MLS, Maritime Launch Services, which will be launching from Nova Scotia. And it's a privately invested company and has cooperation from the Canadian government. The project is receiving their new two-stage design, and it's using non-toxic propellants, refined kerosene or RP1, and liquid oxygen, and they're designating it the Cyclone 4M. Now, a new launch site will be built south of a town called Conso, and it'll have a spaceport that will launch southeast over the Atlantic for sun-synchronous orbits and medium Earth orbits. And launches could potentially rendezvous with the ISS as well. Now, the town of Conso also has a port that they would be able to receive rockets from that would sail from Ukraine and be integrated at the launch site. And Maritime Launch Services hopes to begin launching in 2020 and achieve up to 8 flights per year by 2022. And they're hoping that their whole market will be a lot of the whole global internet / global observation satellite constellations. And they are right now saying that they're going to have a price of $45 million per launch. So if this whole project is successful, then that will place them in a pretty competitive position on the satellite market. And I don't know, I'm really excited because I've been following the Ukrainian progress since the whole Crimean annexation and what's going to happen to their space industry. So I'm really happy to see this. And I mean, it'd be great to have just multiple providers and especially the whole capability of going to the ISS. I really like that idea. So
this is
cool
almost
news.
like a smaller version of like Sea Launch, right? I almost said Sea Dragon
Yeah.
because Vax Hedrum's on later, so like my brain is like already there. I'm super excited about that. But yeah, it's like a smaller version of Sea Launch, right? To a certain extent, or no?
Yeah, in the sense that it's a commercial venture, but different from Sea Launch, whereas Sea Launch was using a mobile platform, the reconverted oil rig platform. This is just going to have a stationary spaceport that isn't going to be out in the Atlantic or the Pacific somewhere. It's just going to be a stationary spaceport. But like Sea Launch, it's a commercial venture that Ukraine participated in to launch their Zenit rockets from that. So
Gotcha. That's really cool. That's so neat. How neat is that?
It's pretty neat.
pretty neat. I think so.
All right, Jared, I looked at the title of this next story, and it bored me to tears, so you're going to have to sell me a little bit on this.
Okay, I will try to sell you on this.
Because, I mean, tears because of dust, but then also tears because of boredom.
Okay.
Okay.
I'll make it non-boring.
Please do.
Here we go. So there's this really cool mission that the European Space Agency is doing called LISA Pathfinder, which is basically testing out gravitational wave detectors in orbit to see if it actually can work in space. So it was launched in 2015. It started at Science in 2016. And it basically, with literally the same day it started at Science, the scientists said, oh yeah, this works. So,
Okay.
literally one day. So great stuff. Now, it uses 2 cubes of gold platinum that are placed 38 centimeters apart, and it keeps them in near perfect free fall within the spacecraft. And what the spacecraft does is it measures the changes in their positions with lasers that are sensitive down to 1/100th of a nanometer. So really, really small movements with these gold platinum cubes. Now they have very precise thrusters on LISA Pathfinder because you need to be very, very careful when you're trying to measure this. If we wanted to change the velocity of LISA Pathfinder by 1 meter per second, it would take 1 week of continuously firing these thrusters in order to do that. That sits out at L1, and like we said, those two cubes are 38 centimeters apart. Now, basically, it ended up proving that, hey, you can do a space-based gravitational wave detector. And now that the primary mission is over, scientists have developed algorithms to scan the data that they've received from it on the probe's thruster firings to find impacts from really tiny dust grains, microscopic sized dust grains that are just floating out in interplanetary space. So they look at these firings of the thrusters because it's an extremely balanced spacecraft. So very, very delicate in how it flies.
Okay.
And you can detect these little microscopic dust particles hitting LISA Pathfinder. And they've got a cool image showing that they can actually characterize things like the velocity, the direction, and the size of those grains as they are coming in. So it's going to continue to collect more data because it's now moved out of the L1 orbit that it had, the L1 being the balance point between the Earth and the Sun, and it's now in a heliocentric orbit. So basically it's just straight up orbiting the Sun. And this is just a really cool way to take a spacecraft that's done with its primary mission and give it a new mission and see if it can detect interplanetary dust, the directions it comes from, and the density of it, which is something that we actually don't really know too much about. So
if we get all this information, because sometimes there's useless information. Like
yes.
Getting information for information's sake, which is not what I'm saying, that this is what's going on. So we go, cool, there's this kind of dust and this kind of dust and this sort of dust, and it's all hitting from these sort of directions in this general pattern. What does that give us?
Well, that could tell us a lot about the formation of the solar system.
Okay.
Because most of the dust that is out there in interplanetary space comes from comets. And comets, they kind of belch and spew dust and gas all over the place, and that gas kind of dissipates, but the dust stays there. So you can actually measure the directions of dust, and you can figure out basically concentrations of where comets are coming from. And from that, you can then apply that to models for formation of the solar system, so you can understand it a little more precisely.
Thank you.
Very cool stuff.
I appreciate
And wouldn't that even help in interplanetary journeys to know if there are large pockets of micrometeorites that if going through at a certain speed would definitely puncture whatever hole you have, and that information might be useful to know, okay, which areas are really populated and which areas do we need to avoid. And at the same time, with the gravitational waves, knowing what other influences there are out there that may get your interplanetary spacecraft off course and have to do correction burns to go to whatever target they're heading to.
It could very precisely tell you just how much gravitational pull a planet is putting on your spacecraft in the area around the Earth, which if you really need ultra precision, that's something that you do have to think about. And with LISA Pathfinder, because it's such a precise spacecraft, that's something that they had to think about. So very cool stuff that they did with it.
Interesting.
Very interesting. Not boring at all.
No, not boring at all. But thank you. I looked at that title and was like, I don't know why I'm caring about this right now. Oh my goodness. Okay. So Mike, we actually, you missed part of the debate about this earlier. We were trying to figure out if there were actually launches this last week. And Dutta and I were like, no, we thought something totally happened. But I think it was actually, this is what happened. And we sort of mistook this information as being a launch. So how about you fill us in on what happened this week?
Okay, so last week there was a launch of the Tianzhou-1 cargo spacecraft, China's first cargo spacecraft that they are sending to their science module, Tianyong-2. So that launched last Thursday on April 20th, and then it docked on Saturday to the Tianyong space module on, Saturday, April 22nd. And we have the footage of that docking.
Awesome.
And with this, yeah, it actually pretty nice footage of of the whole docking sequence here. And I like how last time I said I wonder if we'll be able to tell the difference because the design of these two are so similar. And the Tianyong module has kind of a black cap in the front. It's the module on the left there. And the module we see on screen now is the Tianzhou. It's just white all the way. And the Tianzhou only has 3 panels of solar panels on each side, whereas the Tianyong has 4 panels on each side of their solar wing there.
In
so
other
they were
words,
able
it's like
to
telling the difference
dock.
between the different space shuttles, yeah? Because they all sort of look alike. Just kidding.
Yeah, I can't tell. I can't tell.
Sorry, go
Now,
on.
the
You
whole
were saying.
reason that they were doing this whole experiment in the first place is to test out refueling of their spacecraft. And they were actually successfully able to complete that test this week on Thursday, April 27th. And they were also simulating cargo, which you saw footage of the simulated bags in there. And this is all leading up to their multi-module Chinese space station. And it turns out that they're actually pretty far ahead in construction of the first core module of that space station. The first core module is going to be called Tianyong, and you're seeing it undergoing fabrication and testing right there. That is the real module that could launch as early as next year, although the official plan, the official schedule is to launch it early in 2019. But they're pretty far along in the construction of the flight model. This isn't the test model, this is the flight model. And something else that I'm really excited about is that now that we kind of have seen this design, because it was really hard to get information about what the exact design of it does, it really looks really similar to the Russian Zvezda and Salyut modules.
Yeah.
And yeah. So I'm really excited about this. This is cool information, cool progress, and they are already, they're going to have construction of their space station finished by 2022, and they're inviting their international partners. ESA and Russia have both approached China asking to be a part of their future human spaceflight program. And they have extra docking ports available if their other partners want to participate. So I'm really excited about that. And I'm just, even though as an American, we're kind of competing with them, I'm still really excited to see progress like this.
Interesting. So there's a question that came in through the Twitch chat room from, I think it's BR Spies. I'm going to go with that. It says, this ship is much larger than Progress, right? Do you know how it compares to TKS or Zarya? Zara? I don't know.
Zarya.
Thank you.
Yeah.
Or the like. I mean, yeah. Can you put that in some sort of perspective for us?
Sure. So the Tianzhou and Tianyong by extension are roughly the same size of the ATV module. It's kind of like this in between the Japanese HTV and the European ATV vehicles. So it's not quite as big as a TKS, but it's definitely bigger than a Progress vehicle. Definitely at least twice the size of a Progress vehicle, but smaller than a TKS vehicle.
And part of
and
that
a
video,
TKS vehicle is the first Russian segment of the International Space Station, for those of you who don't know what a TKS is.
Yeah. Well, and in that video, you could kind of see, like, as the part of the module is spinning, you could see people kind of along the bottom. That gives you some perspective,
Sense
at
of
least
scale.
a little bit.
It's
Yeah,
big.
some scale. Yeah, that was really cool, though. That was really, really beautiful. Yeah. Oh, and I want one of those jackets. They look really awesome.
Yeah.
Okay, so, Jared,
Yes.
I personally am very excited about this next story.
I love this next story too.
This
It's
is
fantastic.
So great. So,
Yes.
tell me about all the things I want to hear.
Yes, so NASA astronaut Peggy Whitson on the International Space Station set a record earlier this week for the total amount of time spent in space by an American. Now this morning she has 539 days. Now she's the commander of Expedition 51 on board of the space station right now. This is her third long duration stay. Her first, she was a crew member of Expedition 5 in 2002, and her second one in 2008 as a part of Expedition 16 saw her become the first female commander of the International Space Station. Now she's going to wrap up her mission early in September, and she's going to accumulate nearly 666 days on orbit, which will make her 9th all-time overall out of anyone who is an astronaut that has spent time in space.
That's insane.
She also has the most spacewalks by a woman, most amount of EVA time by a woman. There's just a huge, she is like the king of the lady astronauts pretty
Yeah.
much. So
The Queen.
excuse me, the Queen. I'm
of
sorry,
the astronauts.
the Queen of the astronauts.
I suppose,
in
but I
NASA,
think you
so-
said king because a king is all ruler. Queen still kind of has to answer to somebody to a certain extent.
She's the best.
She's the best.
So
Peggy's
that's the
so
way to put it.
awesome.
Yeah, Peggy's great.
I had girl crush on her a little bit. Oh my goodness! All right, and then before we go into break, that's still an accurate description. Mike, we have a Google Lunar X Prize update, which is really exciting because we haven't had one of those in a while. So tell me some more things
Yeah.
about that.
Well, I have a little bit of good news and a little bit of bad news. Which
All right.
would you like first?
Maybe bad news first.
Let's go with the bad news first. Okay, so there are some unconfirmed reports coming out, and I say unconfirmed because the team that this is about and Google Lunar X Prize itself haven't come out with any formal announcements about this.
Sure.
But these reports that have been coming out say that the Israeli team, SpaceIL, is having difficulties having their lander to be ready in time to integrate with the SpaceX Falcon 9 rocket to launch to the moon before the end of this year. And they have until December 31st to launch, otherwise they'll effectively be disqualified from the competition. And until more info is released, we can hopefully assume that the team will do everything in its power to try to launch on time, or even to find an alternate vehicle somehow, although probably the only thing available to them might be the Shavit rocket, which is a solid rocket that Israel itself produces. And they supposedly have financial support from the Israeli government, so they hopefully will do as much as they can to get that ready in time. But that is the news as far as SpaceIL is going on, that they're having that delay having their lander ready in time.
Do we know why? If they already have the financial support from the government, is it just literally a manpower thing? Is it they don't have the parts? They don't, you know what I'm saying?
And this might not even be a problem with SpaceIL itself. Their
Sure.
lander, they might even be able to have their lander ready, but the problem might be flying it as a secondary payload on a SpaceX rocket. With the delay last year from the pad explosion
Right.
pushing a lot of the launches back, SpaceX just might not be able to accommodate them with their current schedule. And I don't know exactly what is going on behind the scenes, and I don't want to speculate about it, but even though this whole report is essentially speculation.
Still, though.
But regardless, they haven't officially been dropped from the Google Lunar X Prize yet. So this report came out a little while ago, and there haven't been any official announcements since. So that tells me that behind the scenes, they're trying to work as hard as they can.
Sure.
So I hope that SpaceX and SpaceIL are both trying to be accommodating towards each other, and that this mission still goes off successfully. I want to see as many teams as possible try to win this competition.
Totally. A little bit later on this year, we'll have to have somebody from the Google Lunar X Prize on so we can really dig deep into some of these things. All right, but you have some good news, and that's always positive.
Yeah.
So tell me that.
And in good news, this is actually about a team that dropped out last year.
Mm-hmm.
And what I'm talking about is Astrobotic. Astrobotic recently won a small business award from NASA worth about $125,000 to create a modular, standardized small rover that weighs only about 2 kilograms. And their current line of rovers are around 35 kilograms. So not sure exactly what that's going to be, but based on this image from their Peregrine lander, I added emphasis onto the multiple rovers that they would deliver to the moon in a single launch. And I especially wanted to kind of make notice of the really small rover that is in the kind of bottom right corner there. That could potentially be what they're going to base their design off of. But in any case, I'm really happy to see that some sort of business for a former Google Lunar X Prize team, and I hope to see a lot more of the former teams continue to progress forward with their dreams and plans and actually be able to do lunar services. Moon Express wants to do a bunch of services to the moon. I hope that part-time scientists continue, especially since they had their endorsement sponsorship from Audi. And even Astrobotic itself, partnered with, I believe it was Northrop Grumman and DHL, the package deliverer DHL.
Mm-hmm.
So they have those sponsors. So I'm hoping that they'll continue with these projects and still market and hopefully have some customers, as they claim. They claim to already have have hundreds of customers for at least small payloads to deliver these packages to the moon. So I really hope that even though a lot of these teams dropped out, that they will still try to make progress and continue moving forward, and hopefully more mergers and have actually capable companies. So.
Totally. I love not that I don't love the other sponsors, but I particularly find hilarious that DHL would sponsor. There's something about the package delivery thing, the irony that I would just sort of sink my teeth into.
DHL Moon.
Yeah, right? There's just something
if you
about
go
it.
back to that picture, if you go back to that picture actually, and to the left, right above the rover there, there's actually a really small box there that you guys might not see, but those watching at home could probably see it says Moon Mail on it.
Oh,
So
I love it. That's
they're
so
already
great.
thinking of stuff like that.
Very cool. Very, very cool.
Got to keep your package weight as low as possible to get it there. So.
That's right. That's right.
Goodness. So many things. Okay, so what we're going to do is that we're going to go to a break, and when we come back, Ben has a great interview lined up for you guys with our very own Vax Headroom. Stay with us. We'll be right back.
Look into her face, determination in her eyes. She won't give up or quit or fumble little fashion lies. Filled with awesome expectation, this girl's a fascination. And nothing in her way will keep her from her destination. 'Cause she's fire walking, she's fire walking. When it's hot, she keeps on moving. Through the heat, keeps on improving. Yeah, she's fire walking, she's fire walking to be free.
And welcome back to Station 204. I'm coming to you live from the observation deck. I'd like to, before we get into our interview, I'd like to give a shout out to all of the patrons of Tomorrow who have helped make this specific segment of this episode happen. These are people who have contributed $10 or more to this specific episode. We've also got our Orbital subscribers. These are people who have contributed $5 or more to this episode. To find out how you can help crowdfund the shows of Tomorrow, head on over to patreon.com/TMRO. All right, we are now joined by our very own Vax Headroom, Emory Stagmer, who has been on the show many times in the past. One of my favorite episodes you ever did, Emory, was Sea Dragon. You can just search YouTube for TMRO Sea Dragon. That was absolutely incredible. But today, you're going to be talking about reaction wheels and reaction spheres because you're working on something like that.
I am.
Let's start off with what the heck is a reaction wheel?
Okay, so a spacecraft, assuming that it doesn't try and fly simply on propellant, which L-Cross did. L-Cross didn't have reaction wheels. But if you need to be able to have a satellite that's 3-axis stabilized so you can control where it points, like if I want to look at the ground, I have to be able to control very exactly where the spacecraft is pointing. So to do that, I need to be able to control its yaw, its pitch, and its roll. And I need essentially a motor to do each one of those things. Reaction wheels work like if you've ever held a power drill or a circular saw, and when you turn it on, you can actually feel the frame jerk in the opposite direction of the, like in the saw, saw cut this way, you actually feel the motor go the other direction, equal and opposite reactions. And thank you, Sir Isaac Newton. So what you get for reaction wheel systems is a DC motor, runs on batteries, and it has a weighted wheel on it. And it's just a big disc that's heavy around the outside rim. And when the wheel rotates one way, the spacecraft rotates the other. And the rotation amount of the spacecraft is proportional to, it's like a ratio of, the weight of the spacecraft versus the weight of the wheel. And it only works when you accelerate it. So it's the constant velocity, won't change the spin rate of the spacecraft. You have to accelerate the wheel, and then the spacecraft will rotate in the opposite direction. So you need one of those for each of yaw, pitch, and roll. They also have a configuration where they'll either fly a fourth wheel that's in an oblique axis, so that if you lose one of the first three, you can still have control over all three axes. Or they'll actually fly them in a tetrahedral arrangement, kind of like this and that, or kind of like a tetrahedron, which is, a four-sided object. So they can configure those wheels in a number of different ways, but that's how they control how a spacecraft points. It doesn't consume any propellant when you do that. It only takes electricity.
So the reaction wheel is kind of working with the reaction control systems well, not necessarily in tandem, but like are the reaction control systems using propellant traditionally, those are going to be for larger maneuvers in space, generally speaking,
Right.
whereas the reaction wheels are for those more finite, like I've got a space telescope, for example, and I just need to tweak it ever so slightly just to make sure that it's pointed at that star. I generally use more something like a reaction wheel for something like that as opposed to a gas thruster to try to point it. Is that a fairly safe?
Yeah, gas thrusters are not very accurate. The amount of gas that comes out and the amount of thrust that you get out of them is not very predictable. It's somewhat predictable, but it has a lot of variance. If you need to be able to control a high-end telescope, things like Spitzer or Hubble, you need to be able to have a very small, what they call an error box. So I want to stare at this star, and the scientists will say, in order to be able to get the science that we need, you need to be able to point at that star plus or minus some angular error. In the case of the big telescopes, that number is in single-digit arc seconds, and that means that an arc minute is 1/60th of a degree. An arc second is a 1/60th of an arc minute. So an arc second is 1/3600th of a degree. So it's, if you how many arc, I don't know how many arc seconds there are in a full circle, but it's 360 times 3600 arc seconds. So you're talking about a very small change in angle, and you can't get that good with a thruster. You need a piece of electronics that'll do that. That'll give you a very predictable amount of acceleration so that the spacecraft can change where it points.
So you covered some of the downfalls and pitfalls of reaction control, like gas thrusters. Now those are better for, like, if you need to do a very large course correction. You're going to want to probably use a gas thruster for something like that, as opposed to, you could technically use a reaction wheel, but depending upon what you're doing, one or the other may make sense. But what are some of the downfalls then of reaction wheels as opposed to anything else? Like, what are some of the pitfalls of putting those on spacecraft?
Well, one of the problems is if you remember, the Spitzer Space Telescope has currently lost 2 of its 4 reaction wheels. So it's running in a very degraded science mode. And the problem with the reaction wheel is that the bearings wear out. Those things spin at a fairly high rate, thousands of RPM, for years. And if you think about the torque that's going on between 2 different wheels, for instance, if I say I have a wheel this way and I have a wheel this way, if I rotate this wheel, the spacecraft wants to rotate the other direction. The problem with that is the wheel is spinning this way and it has a lot of angular momentum. It wants to stay right there. If you try and torque the spacecraft, you cause wear on the bearings, because the spindle attached to the spinning object wants to stay stationary, right? And so as you do that, so whenever you change any other wheel, every other wheel wears, okay? And so Spitzer, for instance, is, like I said, is running in a degraded science mode. They replaced the reaction wheels in Hubble at least twice, because they were up there for multiple servicing missions. And there's been other very notable failures of large observatories, or expensive observatories, that have, lost their ability to do science, or at least to do high resolution science, because their reaction wheel bearings wore out. So, yeah, that's one problem with them.
Green Jim asks, can you use magnetic bearings so they don't wear out as fast?
They do.
Oh, and they still wear out.
Yes, they do.
All right, so that's some of the problems with reaction wheels, but you're working on something called a reaction sphere, which sounds cool and is fun to say. What is a reaction sphere?
So instead of 3 cylindrical motors, conceptually, if you take the volume of a motor this way and a motor this way, and you cram the 2 of them together, and you take a motor that's this way, and you put all 3 of those together, you can conceive of you have 3 different circles that go all directions, and now you have basically a spherical object. So my concept came from the problem we were trying to solve, where reaction wheels also can't be mounted in very small volume. We were trying to make, this was in 2004, so at the time we were trying to figure out how we could make a 1 cubic foot satellite. It's 3 axis stabilized. And the reaction wheels at the time, they're about, this big. And you can't mount them kind of very well. They have to mount at, here and here and here. And the problem with that is it takes a lot of volume. So anytime that you have more volume, you have more mass. Anytime you have more mass, it takes more power. Anytime you have more power, it takes more volume. It's like the rocket equation. The more you have, the more you have, right? So the idea of being able to take the 3 reaction wheels that you need to control the spacecraft and cram them into the same volume meant that we could shrink the volume considerably. So the initial goal was to reduce the volume. But as it turns out, the concept I came up with for controlling that sphere was unique. Nobody had ever done it quite that way before. Reaction spheres are not a new idea. They've been around since the very early 60s. There was a paper written in Germany, I think 62, that NASA translated into English in like 63 or 64. Honeywell actually basically patented that concept almost verbatim from that paper in 1986. But I never saw any material anywhere that said that they ever built anything with it. Certainly they never flew one. Other people have talked about different ways to build reaction spheres over the years, and there's been patents in the early and mid 2000s. And there was one in, I think, like 2011, where they had the different ideas in terms of how you build the control systems, how much magnetic power that you have to have in order to float and fly a sphere. They're trying to magnetically levitate the sphere, not just control how it rotates. So anytime you have a rotating magnetic field like that, it takes power to rotate the power field. So you go from this coil to this coil to this coil to this coil. Well, anytime you change those coils, it takes power, even if you're not torquing the motor or anything like that. And so the problem becomes one of power consumption when you're trying to both magnetically levitate a sphere and also control how it rotates. Our concept gets away from that because we use very small pulses, and we essentially decoupled the containment of the sphere from the control theory.
So what does that mean, decoupling the containment of the sphere from the control theory?
So you don't have to use the same controls that you use to move the sphere around in order to keep the sphere where you want it, right? So there's essentially an electrical and control solution that's separate from the mechanical mounting and containment solution of what do you do with the, this rotating sphere that's spinning at potentially thousands of RPM. And so we filed for and were awarded a patent on the control theory. That was awarded in October of last year. I'm the sole patent holder, so I'm a patented inventor. That's
is this your first? Is this your first patent?
Cool thing. It is my first patent.
Does this make you our official on Mad Scientist then? Like, do you have to have a patent to be officially?
Well, it doesn't hurt. And this thing is mad. That patent is big. The mathematics document that essentially became the patent is 75 pages long.
Holy cats.
And yeah, holy cats. And the geometry in it is extremely thorough. My very good friend and co-worker, Mike Stoddard, is a mathematics whiz and basically wrote that paper, and that paper became the patent. So yeah, I came up with the ideas, and he's one of the several people who really helped me put feet on this thing and make it happen. So the patent is for the control theory, how we push the ball around, how we decide in what orientation is the ball spinning, how fast is it going at that in those various different slices. Essentially what we did was we took a three-dimensional problem of how do you rotate a ball, right? And we subdivided that into multiple, much simpler two-dimensional solutions. So I have a pod that has a ring of sensors and an electromagnet in the middle. And if I decide that I want the spacecraft to go this direction, I want the ball to go that direction. So I make this sensor the active one in my ring of sensors. And whenever that sensor detects a magnet that's on the ball, I turn on the electromagnet and pull the ball that way, very briefly, just long enough to get the maximum torque out of that magnetic field, torque the ball, and then turn the electromagnet off and let the ball coast on by. So it runs in very small pulses that transfer very small amounts of momentum, but in a very deliberate and very predictable orientation. The problem is now, if you think about, having multiple pods and multiple electromagnets and figuring out the mathematics, if I want the ball to spin this way, well, then all the other things have to, spin in all different directions, and we have to figure out how fast it's going. And if it's spinning in this direction and the pod's up here, the RPM is the same as it is at the equator, but because as you get closer to the pole, the ball's rate is spinning slower as you get closer to the pole. So the linear feet per second, as it spins, goes from whatever the RPM is times the diameter up to 0 at the pole, at the spin axis, where the spin axis is of the poles. So figuring out how long the pulses have to be, how fast you're going, what orientation you have to do those things in, the math there is really pretty whacked. And we subdivide.
That's this technical term. The math is pretty whacked.
Math's pretty whacked. It's interesting though. One of the things that I have, I think maybe that you were talking about, but I had heard on the internet was talking about Tesla automobiles and how the Tesla is essentially a software-defined car. This is very much a software-defined motor. It's run by an FPGA, a field programmable gate array that does all the logic on the inside, and it has a large math library on the outside that runs in your main spacecraft computer that decides, what kind of commands I need to send to it in order to do the pulses. But I can reprogram its behavior drastically by changing the programming that's in the FPGA on the onboard, the onboard processing inside the little box that directly drives the electromagnets and the sensors.
I'll be frank, that sounds like both a pro and a con, right? The pro is you can make it do anything you want. The con is that it could accidentally do anything you ask it to do, maybe if you didn't consider that you were asking it to do that.
Yeah, absolutely.
Right? I mean, code can get complicated.
This is complicated. The timing, the orientations, the pulses, how the pulses are done, and other things like making sure that the electromagnets don't stay on too long because they get hot. Those things they have a lot of power in them, and so your duty cycle of your electromagnets needs to stay low so that you can dissipate the heat that's generated while they're on. These electromagnets are pulling about 75 watts, and they are 3/8 of an inch or 3/10 of an inch in diameter. So they're that big around, and the electromagnets are that high, and they generate 75 watts each, and there's 8 of them. So there's a lot of heat generated in electric motors in general. So we have high temp electromagnet wire and copper windings and copper cores and all those kinds of things in order to try and get the heat away from the thing.
And then, how do you dissipate that? Because, part of what you talked about is that part of what you're trying to solve is the reaction wheels themselves are large and heavy, and you're trying to put these on something like a CubeSat or a small sat, and that's just not going to be a thing.
Right.
You bring it down in size, but if you've got a thermal problem, aren't you making it larger in size again? Because in space, where does that heat go?
Yeah, the heat's got to go somewhere, and so generally in these kinds of systems, you bring the heat out to an outside plate of your unit, and then you tell the spacecraft, you need to dissipate this much heat from this plate. How you do that's your problem. But that's generally how it's done. If I have a processor card, that thing is coupled to the top and bottom plate, and the bottom plate of the processing power box has a cold plate on it, and that cold plate is, basically they're pumping the heat, either solid state or even sometimes with liquid coolers, that they pump that heat out to something and they radiate it away into space. So in a CubeSat, that problem's amplified. That's true, but we're dissipating about the same amount of power as a reaction wheel of a similar capacity although we are in about, I'm sorry, bump the camera, 1/5 of their volume.
And so some questions from the chat room, a lot regarding this. If the electromagnets, this is from Green Jim, if the electromagnets generate 75 watts in a very small space, do the algorithms have to take into account that material expansion and contraction due to heat? Because things are going to change.
They're so small that they're not going to go, they're not going to shrink very much. Although we do have thermal sensors on every electromagnet. In our current design, there's 4 pairs of electromagnets. There's one sensor pod for each pair of electromagnets, and so we have temperature sensors on those, so we know how hot they all get. And they have currently we're still running the unit in air, and so the air they have little tiny heat sinks on them, and we'll be blowing air in a chamber to try and while we're thermal cycling it or while we're doing other testing. So it's got some, you got to watch how much you're perturbing it, because that can invalidate your testing. But yeah, we've got to cool them in air. Cooling them in vacuum is a much harder problem, and that's a next year problem, not this year. So
our station commander Dutta asks, could you use some of that heat to help power for power generation?
Potentially, but coupling heat to electricity is very, very inefficient. You only get 5 or 10% of it back, so maybe a little bit, but not much.
And then Warp 11 asks, would it be difficult to change the axis of rotation of the sphere because of gyroscopic stabilization?
The interesting thing about the sphere is that it doesn't matter what the sphere's spin orientation is. You can still push the spacecraft around the sphere in any vector. So if the sphere is spinning this way, I don't have to push the spacecraft back and forth like this. I can push the spacecraft up and down or at oblique angles or anything. The faster the sphere spins, the more rigid it gets in space, and the easier it becomes to push the spacecraft around it. So it doesn't matter what the sphere's spin axis is. And in fact, I don't even try and control the sphere's spin axis. All I'm trying to do, momentum is always conserved. That's one of Isaac Newton's laws of motion. And so what you're trying to do is transfer the momentum from the spinning sphere to the spacecraft body, or back and forth one way or the other. So the spin axis of the sphere doesn't matter. The spin rate of the sphere doesn't really matter, except that you need to know how fast it's going in order to know how long your pulses are, in order to know how much momentum you're transferring for each pulse that you execute. So the physics is peculiar. On the bench, my spacecraft is essentially the whole planet. And so I can't move it around. All I can really do is control the spin axis of the ball. But by the equal and opposite reaction, I'm controlling the spin axis of the spacecraft.
Andrew Shire asks, when does it fly?
We have a tipping point technology award we got from NASA a year ago, and we've been working on that since last July. And so we have it's the tipping point technology programs, of which there are quite a number of awards, and NASA just awarded a bunch more, some of which are very interesting. But they're trying to get you through kind of what's known as the valley of death in the industry. NASA rates technologies based on what's called technology readiness levels, or TRL. And they run from 1 to 9, where TRL 1 is an idea and TRL 9 is a device that's successfully functioning in space. Trying to get from TRL 5, which is a lab unit that has essentially worked in relevant environments, which means you've done some environmental testing, to TRL 7, which means you have a space qualified piece of hardware that's been tested in relevant environments. Trying to get from 5 to 7 is very difficult. It takes a lot of money, it takes a lot of time, and so NASA helps industries try and get those ideas across that very difficult valley from TRL 5 to 7. That's what the Tipping Point Technology Program is. And so we have a 2-year, $2 million contract with NASA that's co-invested by Northrop Grumman to get that reaction sphere technology to TRL 7. Once I have something at TRL 7, getting it to TRL 9 flying in space is not that difficult. This is an interesting project, and people love interesting stuff, especially engineers. And so I already have 3 people that tell me they want me to put a proposal in for technology demonstration missions, even though we're still in the middle of building our TRL-6 unit. That's currently being built right now at our facility in Northrop Grumman. So I hopefully I could see this fly as early as late 2018, 2019.
Well, in a way, it has flown, right? Just not in space.
Well, to get from TRL-4 to TRL-5, one of the tests that we did was we flew it on a ZeroG airplane flight. NASA's Flight Opportunities Office provides all kinds of different ways that you can fly technologies in microgravity in order to be able to test them. And so this picture is us testing one of the 2 units that we did in 2014. We flew 4 flight days and an hour each day and about 60 parabolas a day. So I have almost an hour of ZeroG time. This is one of the parabolas that we did. As you can see, we had multiple cameras. And then the graph on the bottom right is actually the gyroscopic data of the unit that's inside the blue box. And we cross-correlated that with the multiple cameras and the gyro data. So here we're going to show it to you again so you can see the gyro data a little bit more and you can see this unit moving around. Right now, this is the time where we're just at the onset of the ZeroG time, and you can see people starting to, they're currently standing, and then you'll see people start to fly and float. Here's our unit floating. You can see I touched it here. Here it's free flying. You get a nice smooth curve. And then as it comes down here, it bumps against the ground and then tumbles a couple of times. And then you can actually see right there where they actually pick it up and hand it to me. This was actually not a successful test. We did, I forget how many tests we did. I have like 600 gigabytes of high-def video. That was one that we thought was good, and when we did the analysis on it, it wasn't. But I happen to have that piece of video put together that I could give you to show on the show today. That was the ZeroG flight thing was totally amazing. But as you can see in that, I was pretty much just strapped down to the floor. I was very concerned with trying to get, every possible parabola, all the maximum possible data that I could get for these units. So I didn't really get to fly around or anything. Some of the other guys on the team did, but I stayed strapped to the floor most of the time.
A couple more questions from the chat room. I don't have it in front of me, but Neuropilot earlier asked if you're allowed to say which FPGA you're using for programming.
Right now, we're using a reprogrammable commercial device. I don't happen to remember what it is. But right now, it's a ball grid device. Eventually, for spaceflight, we do something that's a higher order technology that most people haven't heard about that's called column grid. So a ball grid, the FPGA, which is only about this big, has several hundred pins on it. I think we have a 400-pin device. And underneath each one of those pads on the device, there's a little ball of solder. And when you reflow the solder, you make it hot. The ball essentially melts and connects the FPGA, the gate array device, down to the circuit board. In a column grid array, you have a column of solder, and you have a helical coil of very small copper wire in that coil. I mean, these things are, a millimeter tall or something. You're talking about very tiny cylinders. And so that allows the columns, as opposed to the balls, have a little bit of flex in them. So if the circuit board changes size, or if the FPGA changes size when it gets hot and cold, the columns allow a little bit of flexibility so you don't break the solder joints. The balls will actually break under thermal stress. So if you look at those things under a microscope, the column grid array from a side point of view comes up and goes out at the device and goes out at the bottom. So they have a flare out onto the pad and a flare out onto the pad on the device. And so they make a very rigid connection. Like I said, there's a helical coil of wire wrapped around that column of solder. So what we would eventually use for space flight is very expensive parts. Those are more than $5,000 a part.
Well, so do you have to use the expensive parts for spaceflight? I mean, when we're talking about CubeSats and whatnot, part of the goal, I would, not always, but part of the goal is to reduce the cost of those satellites, bring them down, make them smaller. Can you just use the COTS parts and the smaller stuff for a CubeSat? Or is that just really not going to work?
It might work. It probably worked for a while. But as soon as you run that through, a year's worth of day-night cycles in orbit, where they get hot and cold and hot and cold and hot and cold, you're going to break the solder joints.
But
it's going to fail.
So then it depends on the CubeSat. Because if the CubeSat only has a life in space of a year or less, then maybe you don't care.
You're probably okay, yeah. But if you want it to be, if you want it to be a high reliability mission, you want it to last 3 to 5 years, you want it to be, an 80% likelihood that at the end of 5 years that it's going to still be able to work correctly, you're going to need the high reliability components.
Jaded Animal from our Twitch chat room asks, how big could you make such a thing, without losing the advantages? And I think to that same point, not just size, but let's look at it more from a, how large of a spacecraft could I keep orientation on?
Pretty big. The current size that we're building, we're actually using a billiard ball. So that gives you an idea. We're designing it to be flown on a CubeSat and for our first demonstration flights. So we have a 2¼ inch diameter sphere, and there isn't any reason that it can't be as large as you would want it to be. I could conceivably build a reaction sphere that would control the International Space Station.
Okay, out of curiosity, how large would your reaction sphere have to be that controls the International Space Station? / I feel like that's the beryllium sphere out of Galaxy Quest is what that would end up looking like.
We've joked so many times about building it out of beryllium. It really is. It would be larger than a 10-pin bowling ball. So, you're talking about a sphere that would probably be on the order of that big, and it would probably take several of them. Nice thing about that is, they're completely redundant. So each one can control the spacecraft. Then it's just a question of how fast do you need to turn it? How much torque can you generate? How much momentum can you store? But the second one could control the spacecraft just slower, even if you lost the first one. So you don't lose... The things are very resilient the way we've designed them. You can lose electromagnets, you can lose sensors, you can lose significant portions of the electronics, and it would all still work just fine. You would just be a little bit degraded, but you wouldn't really lose any control. You'd lose the amount of control. But being able to fly multiple units in a spacecraft, they would look like, to the spacecraft control systems, it would basically look like you had one big device in the center of mass, whatever the mass of the spacecraft is. The spacecraft's always going to rotate about its center of mass. So if you had a cubic-shaped spacecraft that was, a cubic yard or something, a cubic meter, a pretty good sized thing, you could put a small reaction sphere in each corner and have 8 of them. All you have to have is knowledge of in what orientation you mounted them, and then you'd have 8 times the control authority. And if you lost, you could run it with 1, or you could run it with all 8. It's just a matter of how much power you wanted to consume.
So the station commander has another question. Dud is asking, is the sphere's makeup a consideration? Can you use different material densities to be able to get more oomph out of the same size sphere? You mentioned bringing the volume down, but you could leave the mass the same as a reaction wheel if you wanted to, right? Or even find a material with greater mass. But then adding on to that question, is it really the mass that makes a difference, or is it the velocity of the sphere that makes a difference? Or, probably
the
both.
amount of momentum that you're storing in a sphere, the equation for that is 2/5 times the mass times the radius squared times the current spin rate. Okay, so radius matters a lot because radius is squared in the equation. The mass matters linearly. Okay, so if you have twice as much mass, you can store twice as much momentum. So if I went from a sphere that was made out of a billiard ball, which is 7 ounces, to something that was made out of tungsten that weighed 5 times as much, I could store 5 times as much momentum. Okay, it would weigh 5 times as much. The interesting number is the number on the front, the 2/5 number. That's essentially what do they call that? I think they just call it a figure of merit. It's essentially has to do with the geometry, because if you think about the spinning mass, the thing that really matters in the spinning mass is the outside edge, right? And because that's what's got all the speed in it. The center of the mass, if it's a sphere, doesn't, the entire column of material that's along the axis doesn't buy you anything. It's just heavy, right? It doesn't provide you any angular momentum. So a reaction wheel, which has a cylinder, if that cylinder is a solid squared cylinder, right, squared off cylinder, that figure is 1/2, not 2/5. 1/2 is a little bit better than 2/5. So what they do is they generally will thin those reaction wheels out in the middle and only have the majority of the mass around the outside rim. Mm-hmm. Well, that number gets closer to 1. If you have if you had an infinitely thin rim around the outside, that figure of merit goes to 1 because you don't have any wasted mass in the middle. So to build a hollow sphere, we can probably get that figure of merit up to about 3/4. And so our next generation of spheres will probably be a constructed object rather than a billiard ball where I've bored holes in it and stuck magnets in it.
And made of beryllium.
Actually probably tungsten because it's got a lot of mass and I can make that shell really thin and have the same amount of momentum that I can get out of something that's a lot more solid or something. So I can have a lot better, momentum storage.
When do you, kind of getting to the end of this part, when do you expect to be able to fly some of this in space?
Like I said, we've got 3 proposals people have asked us to return. We have requests for proposals. We have 3 of them now, and we're working on filling those out. I got to get some of them in by week after next. So they could be next year or the year after.
And then when you're done with this project, will you be moving on to working on building Sea Dragon for real?
I would love to build Sea Dragon for real. I think Reaction Sphere is my life for quite a while at this point. It's my idea. I'm the integrated product team lead. I have the patent. The nice thing is I have a manufacturing group and I have other folks who are working with my engineering team who are doing a lot of the work. And so I've worked through some of the manufacturing steps with the manufacturing guys for the first unit, and they're building the second one on their own. So I don't have to get involved in everything, and eventually it can become a product line for the corporation where I would be involved in product updates and maybe sales, but I wouldn't really be doing day-to-day engineering on it.
All right.
Who knows what I'll go to it.
Let's move to our general questions before we go to break. I don't think we've actually ever had you answer these before. Correct?
Yeah.
I think you hadn't been on since we started.
Oh yeah, I have.
Oh, you have. All right. Well, we're gonna.
I think the SmallSat interview where we talked about the Northrop Grumman SmallSat electronics was the first time you'd actually used this.
So now here's going to be the interesting thing. So now you're going to get to do them again, and we're going to see if your answers match. This will be a fun one because I guarantee you we're going to bring you on again in the future because you do interesting, cool things. And I will be curious to see how time changes your view of space. So all right, let's go. Yeah. Moon or Mars first?
Moon.
Would you go?
In a heartbeat.
When do you think humans will first land on Mars?
In the early 2030s.
When do you think humans will first? I did that again. I have to stop doing that because the conspiracy theorists will get me. When do you think humans will land on the moon again?
That could be in the late 2020s.
That's
5
coming
to 10
up.
years from now.
Yeah, it's coming up.
5 to 10 years. Yeah.
And why space?
It's the next frontier. It's the thing that inspires people. It affords us opportunities, the same kinds of opportunities when people were expanding into other unknown territories for resources and for science. So, if you stand outside and look at the moon at night, imagine looking up at a moon that's it's a sliver waxing moon and being able to see lights up there where you can say there's humans living on that. That would be really an amazing thing. And it inspires kids. I go out and I talk to, I read books to what are they? They're second graders once a month. And I started taking them space and science books, and man, you can't get those kids off of asking questions. They always have questions about space and science, so it's really fun. They're very inspired by it.
All right, Vax, where can people find more information about you and your reaction sphere?
There's a number of links for the reaction sphere. If you just search for reaction sphere on Google, you'll find things from NASA. Northrop Grumman hasn't put out a lot of information about it yet, but that's probably coming in the next 6 to 9 months. You can go find the patent, of course, and if you want to find more information about me, I'm at twitter.com/VaxHeadroom.
All right, awesome. Also, Carrie Ann and someone else in the chat room, Smokey Durgan loves your button, the coffee-based life form. I think that's pretty. Form. So, actually, one final question before we go into break. What is your favorite coffee?
Oh, my favorite coffee.
And you've got the tomorrow.
I have it tomorrow.
Yeah, look at that. Yeah. Nice. Sweet.
Shiny. I don't know how many of those are out in the wild. I don't know how many of those you've
Not many. Is it the blue one or the black one?
Blue.
Oh, yeah. Very few of those. Very few of those.
Yeah, I got one of these like first day they were available.
Yeah.
Favorite coffee. I drink Cafe Americano, so kind of depends on where I go. It's generally Starbucks.
All right. Thank you, Vax, so much. I'm sure we'll bring you on in the future. You do really cool things. You're always full of interesting stories, and I really appreciate you taking time out of your Saturday, especially last minute, to come on the show. Yeah,
sure. I'm sorry Mike Milling's not on. I'm looking forward to having him back. Hopefully you get him rescheduled.
Yeah, absolutely. We're working on that rescheduling right now. So yeah, we'll hopefully have him. We're trying for the end of this next month, but we'll see. All right, we're going to take a quick break, and when we come back, comments from last week's show. Stay tuned. We'll be right back.
We've always looked to the stars. They guide us, give us comfort, help us find our way. We see ourselves out there. When we look up, it inspires us. And we long for something we don't yet know. We yearn to go there. So, we venture forth.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills.
Tranquility Base here. The Eagle has landed. It's one small step for man, one giant leap for mankind.
The exploration of space will go ahead, whether we join in it or not.
Many think we stopped exploring. But we know our journey didn't end.
T-minus 1 minute.
We've only just begun.
Orion is functioning perfectly at this point.
Come with us and explore tomorrow.
And welcome back to Tomorrow. Now, before we get into comments from last week's show, I want to give a shout out to all of the patrons of Tomorrow who have helped to make this specific segment of this episode happen. These are our Escape Velocity members. It's $10 or more. They get access to absolutely everything, including the Slack, and we're also testing Discord, so that's kind of fun. You can also get, we've also got our Orbital subscribers. These are people who contributed $5 or more, and they're going to get access to basically everything but the Slack / Discord channel. And we've also got our suborbital members. They're going to get access, them and everyone above, to After Dark as soon as it's made available on demand. To find out how you can help crowdfund the shows of tomorrow, because that is how we make these shows happen, head on over to patreon.com/TMRO. All right, Capcom, we brought Space Mike into the observation lounge for the first time, I believe. Does it feel different out here? Does it feel different out here?
It does.
Yeah, a little.
I feel giant-sized, and like if I stand up, I might hurt the ceilings. So we don't need a cabin depressuring here.
All right. Let's talk about that last week's show, Capcom. We had Lisa talking about Cassini.
Yes, Lisa Tadgy.
Our longest show ever in the 10 orbits we've done this.
Yes.
Correct? I
Yes.
believe it was just a pinch under 2 hours, worth every minute of it. One of my, if not my, mostest favoritist shows.
Yeah, it did.
It was.
didn't
It
feel
was.
like
It was in my top. You know, it really didn't. Like we did the interview. I was like, oh, that was a fun 20-minute interview. No, it was like an hour or something.
Yeah.
It
Yeah.
was. It was. If you haven't seen that show yet, definitely go back and watch
Yeah,
it.
not the fourth, not the third, not the tooth, but the first longest show we've ever had.
Am I ever going to live toothed down?
I don't think
That's
so.
not going to be a thing.
I don't think so.
Thanks, Jared. That's
You're welcome.
fantastic.
You're welcome.
right.
Tried to get it in every show.
Oh my goodness.
Is that going to be our Easter egg from now on? Trying to roll toothed into each show?
I think so. I think so.
Okay. We need, all right. I'll talk about that later. I'll talk about it in After Dark. Some of the, I want a martini or something. I want like a
Alcoholic beverage.
alcoholic
Good
beverage.
God, I do too.
God, all right, Capcom.
You sure?
Yeah, I'm sure. I know. I keep throwing it to you, and I know I'm a terrible human being.
Okay, first comment comes off of YouTube.
Okay, now let me just.
I'm going to hit you on air. This one comes from Mark Thornsby. I actually agree with SpaceMike's original excitement regarding the SLS, or Space Launch System, and the new exploration schedule. There is more reason to think that the SLS plans can actually be accomplished than the other plans from the past. Even if SpaceX takes over and the SLS is doomed, the schedule can still be accomplished by purchasing launches from SpaceX. It's the exploration that matters. We should be excited, believe, and plan in the impossible. Isn't that the NASA's DNA? Ben?
Yeah.
Well, I mean,
Mike?
So, Mike, you agree, right? I mean, you're excited about all this.
Absolutely.
Yeah,
Yeah, absolutely.
I don't think so. I mean, let me be frank. The whole point of this show is to get people excited about space. That's why we're here.
Yep.
If Space Launch System gets you excited, then heck yeah, Space Launch System, ready, go. Let's do that.
Sure. And sure. I can't even believe that I'm the one who's taking this stance right now. Yes, but no. But yes, but no.
But that's how everything is. It's I
Sure,
mean, it's
I
all
just-
trades. It's always trades, right?
Yes, that's fair. And we should have a wish list. NASA should have a wish list. Whoever should have it, like Jared was talking earlier, there should definitely be a wish list and a bucket list or anything along those lines. There should be those sorts of things. However, you do have to keep grounded in the idea that NASA isn't the one who gets to make their own decisions.
Yeah,
it's not
that's
like,
true.
let's give money to NASA, NASA gets to do what they want. No. That's not the way that this works. This is more like a parent giving a child an allowance for something very specific. It's not like, sure, you can spend that on candy. No. It's you can maybe buy a single piece of candy, but the rest of that has to go into the fund for that Hot Wheels thing that you want.
So I think TWicked actually nailed the general idea of our issue with SLS.
Yes.
Which is SLS will eat up over 20 billion in total, with each launch costing at least 1 billion. So if we look at SLS and we ignore the price tag for a moment, SLS is amazing.
Sure.
Right? SLS is going to enable humans to do incredible things in space.
Right.
Ignoring the whole Senator's design, blah, 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 its payload to low Earth orbit, its payload to GTO, its payload to Mars and the Moon is awesome.
Sure.
It's incredible. I guess my personal only gripe with Space Launch System is it's so freaking expensive.
Yeah.
They have to find a way to get that price down. They have to find a way to get that price down. And I don't know if the government is capable of doing that, right? The government is not known for having to be competitive on pricing, right? They have taxpayer dollars. They don't have to be competitive. So I'm not sure that's something they're going to be capable of doing. Neuropilot, how could they reduce the cost per launch of Space Launch System? It's going to be, in my opinion, having not seen anything, so this is based on not real data. Actually, let's go around the room and see how they think you could do it. I'll start off with saying I think it's going to be developing the manufacturing processes to ensure that they can just crank these things off the assembly line quickly and cheaply.
Right. This has to be less of a jobs program than Shuttle was.
Yeah. It's
Has
not
to
about
be.
hiring people. It's about creating the robots to automate the whole process,
Right.
making sure that it's the same every time.
Yes.
Right. That there aren't flaws with it, and just cranking them out of moving them through the production workflow as fast and as stable as possible. If they can create that, then you've got your high upfront investment of the machines that make them the machines, but now you can just make the machine repeat.
Well, that and let's just take SLS as a program altogether. There are very specific things that they are being told that they need to use. There are very specific companies, there are very specific processes, there are very specific areas that they need to work in of the country, for instance.
Sure.
You cut a lot of those things out if you can go with what makes the most sense, what's the easiest, what's the most efficient, and what is going to give you the most accuracy, and that may not actually be the way that it's set up. That's going to take a lot of your costs out. Mike, you had something?
Yeah, to kind of a couple of those points there. I mean, the whole reason that the SLS architecture was planned out was supposed to be to save money, because we wouldn't need to buy all brand new tools to manufacture them. We should have been able to use the tools that already existed in order to build shuttle. That was the whole point, and to reuse the engines that were used on the shuttle, to reuse the tanking. I mean, to use all of this hardware was supposed to make it cheap. And that's what makes all of this so ironic, is that the whole reason this plan was decided on over 10 years ago was because it was supposed to be really cheap. And regardless of whether or not it launches once or twice, I mean, I am not a fan of the cost. I mean, like Ben said, ignore the cost for a minute, and it is an amazing rocket and is a very capable rocket. However, it's that whole cost that really grinds everyone's gears. But the part for me that especially got to me was that what's the payload? What's the payload? For the past 9 years, the only payload has been the Orion capsule. And there was the whole, kind of argument back and forth for Europa Clipper, and now that that's been decided, now that's a payload as well. And why this news story was so exciting to me was here is finally more payloads. Here's an airlock module. Here's a really big cargo module. Here's electric propulsion modules. Here's all these pieces that you need to build your essentially Mars cruiser with, and to actually accomplish the goal of getting to Mars in the 2030s. Here's the plan, here's how we're going to do it, and now there's a bunch of payloads. I mean, now there's 11 different payloads other than Orion capsule that the Space Launch System could potentially use. And I don't care if the Space Launch System gets canceled. I'm fine if it gets canceled. But now I am excited for those payloads, and I want those to be launched one way or another, whether it's on a Space Launch System or any other rocket. I don't care. But the plan of having this lunar space station and assembling the cruisers to go to Mars from that station is really exciting to me. So
Jared?
I agree with all of your points about how the Space Launch System needs to be, it's too much money.
No, I think we're all generally in agreement. I don't think anyone's ever sitting here going, I hate that rocket because it's from NASA. Not. I mean, I think... Right? I mean, the numbers are good on the rocket. The numbers are good.
It's not bad.
And you look at, I think we talked last week about, we're just going to spend the entire rest of the show on this one comment. We should do? Well, here's what's happened is we've, Orbit 10, we've gone to this interview format for the second part of the show, and we've stopped our roundtable discussions. And I have just right now realized that this needs to be a roundtable discussion, because I think there are a lot of really interesting points that can be brought up. We can talk about, how Skylab was 1/3, I said last time, about the same volume or more than ISS. It's actually about 1/3 the usable volume is ISS. So you just need 3 SLS launches essentially to build an entire International Space Station's volume worth of stuff. I mean, that actually ends up being less expensive than what ISS was. So we could do some cool things with that. I mean, there are a lot of really cool things. We should turn this into a roundtable discussion. I think we've decided...
Does that mean you're not going to let Jared talk at all?
No, I am. But I think we've decided what we're going to do is... we're done with him. We don't need to see...
I'm just saying, you were going to go to him. I'm
just going to head on over to Jenna. Real quick.
Okay.
Here's what we'll do. We'll bring back the roundtable discussions any month that has a 5th show in it. Instead of a 4-show month,
Sure.
we'll do it on those.
Okay.
So we'll add this back in, but before we move on, your
2 cents.
Your 2 cents. What could we do to reduce the cost of SLS?
So I'm going to be the pessimist here, and I'm going to say that you're going to be unable to reduce the cost of SLS.
Really?
And Green Gym 2 had a very good point.
Wait, reduce the cost or reduce cost enough?
Reduce cost, period.
Okay.
Interesting.
So,
okay.
Because Green Gym 2 had a very interesting comment in the chat room, which is that if you wanted to reduce costs, you would have built in the ability to reduce costs with Space Launch System. And to me, there is no ability to do that with the rocket.
Is it not
It doesn't seem like anyone is doing anything to try to actually address the costs. If there was something going on with that, then maybe sure. But it just doesn't seem like.
But I think there's a different. The question's different though. It's not are they going to. I think we all kind of well, I won't speak for everyone. I don't think they will. I don't think they're going to reduce costs because again, it's a government agency. They don't have to. But that doesn't mean they can't.
Right? Okay, but that's getting slightly off topic. We're going back to the actual comment was that we should still be kind of excited about what the plan is, what the overall plan is, because even if SLS, again, side table discussion, even if SLS fails or doesn't go or whatever, that those milestones can still be reached another way.
Possibly,
right?
Yes.
That's what the question is.
Well,
or that's what the comment
right now,
is.
all of this is on paper.
Sure.
Right? It's all paper rockets.
Well, I mean, the thing is that Mike was really excited about it, and I poo-pooed the entire thing. So, so there is that.
Well,
I mean,
some of the pieces that I was going to talk about actually exist, like the electric propulsion module that would do station keeping and to initially be the first piece. That's been built. That was for the NASA ARM program, and not the actual one that would fly in space, but the test article that they would be doing some of the vibration and environmental testing with. That's been built. So I mean, that architecture already exists. So if nothing else, that piece at least will continue development. And the other modules for this lunar space station are based off of Boeing's designs for the modules that are used on the International Space Station right now. So it's even though it's still in a paper design, it is very much within the realm of possibility to have those things be built in a timely manner to accomplish this goal within the 2030s.
Your passion is infectious. We're going to move on because we're going to turn this. No, it is. We're going to move on because we're going to turn this into a roundtable discussion. Also, I continually am surprised by your ability to do the hologram look off camera to create the image. I absolutely love that. Next up, Capcom.
Well, Jastro really quickly says, I know a way to reduce costs. Call Falcon Heavy SLS.
But Falcon Heavy is not the same. Okay, this is going to
hilarious.
Roundtable discussion.
Good Lord.
I thought it was funny no matter what Ben says. Good. Next comment comes off of Patreon. From X-Arrow, actually. Great interview with Lisa about Cassini. I remember the news of its launch when I was 14. God, I'm old. What an incredible mission it had.
Oh my God, I am too.
I know. Watching the grand finale video makes me rather sad. It's like putting down an old, dearly loved and loyal family dog. It's for the best, but it's still very sad.
You guys want to feel even older?
Sure.
I was 9 when Cassini launched.
Yes! Yes.
Yeah.
Awesome.
4th grade, baby.
No, the chat room does not need to start going into how young you were.
I can say that.
Also, Mike, you don't need to tell us either. I'm okay not knowing. I'm okay without these stats. He's turning red. I think he's turning red.
Very nice. I don't remember the announcement, but that's because I wasn't really.
Mini Stoge, I didn't want to know from you
yet.
either. Oh yeah, you weren't a space nerd.
I really wasn't. So sorry, I missed out. Sorry, guys, I suck at this game.
Next up.
Next comment comes off of Reddit from Ferdinand.
Ferdinand.
Okay. The cryovolcanoes amaze me. The thought of trying to boil your vegetables in a water volcano on Titan is crazy. Just think about Frodo and Gollum fighting on Ice Mountain Doom. When Gollum falls, instead of dying, he's enjoying a hot bath. I don't think that's the way that actually works. If the water's gonna be hot enough to boil vegetables, it's gonna be hot enough to boil you.
Well, not necessarily.
Yes.
No, that's not how.
I have this burn.
Yeah, but not hot though. Not hot though.
But
it's, remember, go ahead.
No, you were gonna just say the same thing I was gonna say.
Saying, it's a sludge. Lisa was saying that it's like a slushy. You know, it's still ice particles, but it's just gotten loosened up. You know, like molten lava. This ice rock, rock has gotten slushified, and that's what's being expelled. It's not necessarily boiling water.
Right, but you also need to remember that the temperature that water boils at changes based on pressure.
Right. Yeah, but on Titan, the atmospheric pressure is actually higher at the surface than it is here on Earth.
Oh, well, then you're getting toasted. So, yeah, if it's boiling, all right.
Yeah, it's like 1.3 atmospheres at the surface of Titan. So it's thicker. It's thicker than the Earth's atmosphere.
Well, fine. I just got so you knew. Yeah. All right.
I thought we were talking about the ice volcanoes on Enceladus.
No, Titan
has ice volcanoes too.
Oh, there are a lot of ice volcanoes.
We
found a lot of ice. Yeah. We got a lot of ice.
Yeah, it says Titan in the comment.
Vax has some input.
Mr. Vax.
Wait, go. Yeah, we can do that. Look at that. Magic, yes! Oh! Go Vax.
I didn't know that. That's really fantastic. It's an interesting piece of the
I was just having a
atmospheric pressure of Titan. I didn't know how high that was.
Yeah, for some reason I just assumed.
Yeah.
I assumed it would have been a lower atmospheric pressure.
Titan's atmosphere is so thick that if you actually made yourself a set of wings and you ran fast enough, you could actually take off and fly through the atmosphere of Titan.
Okay, that's the shirt for a show. Is a dude like with wings, wooden wings, flying in Titan.
Yeah.
It's got to be a graphic image. Citizens of Tomorrow, I need someone to drop that image for me.
That is super amazing.
All right.
Oh my
Next
goodness.
up, next up.
All right, next comment comes off of Reddit from Chasar1. Shazar1. I think it's interesting that she mentioned a big constellation of Cassini probes around Saturn. If that was the case, the price per spacecraft would probably be reduced due to the economics of scale and the fact that you only design a spacecraft once. I'd love to see a fleet of cheap, mass-produced, general-purpose spacecraft which we can all send, or which you can send all around the solar system with a minimal customization.
I think that would be awesome too.
That would
That'd
be
be
really
sweet.
cool.
Literally a fleet of robotic probes. This is what we have.
Gotta bring me back my hologram. Now, wait.
That's
Vax is working on the.
Nice.
I got to work on the look, right?
Right, that's not bad. That's really good.
There you go. You got it.
bring there. Oh, I see what he was trying to do, but it did not work. He's
No,
trying
it
to
did
work
not.
on a. There you go. All right. We'll get that going for After Dark.
Oh my goodness.
my gosh.
That's hilarious.
That would be awesome. I just don't. Again, it comes down to cost, right? Cassini got very expensive, but I think this is where small sats get really interesting because, we've talked a lot about small sats on the show and CubeSats, and their big problems are power and propulsion. Probably in that order because they're kind of linked. It's 50-50. If we can figure those things out, and things like Vax's reaction sphere will help. There we go. Vax's reaction sphere will help. We could start sending these to other planetary bodies out in our local system, right?
Yeah, I'm just
and
laughing
then-
at our two holograms looking at each other. Like, not only are they looking at us, but they're looking at each other.
After Dark has started early for this show.
Amazing!
Oh my
this is
So
God.
good.
This is weird.
So good, I
Don't
love
make it weird.
Oh, it's
Don't make it
already
weird.
weird. You know what? I think, yeah, it would be really cool. Let's do,
That would be.
let's do one more, and then we'll head to After Dark.
Okay, because there's two more. So you want me to only do one of those
Yeah,
two?
just do CO6.
Okay, perfect. So then last comment comes off of YouTube from the capacitor. Or capacitator? No, capacitor. I'd spend hours just staring at Saturn through a telescope during freezing cold nights as a kid. Where the hell do you live? It's always been my favorite planet in the solar system, mainly because it's the very first planet I have seen through a telescope. After seeing it in books, magazines, documentaries for so long, then I finally point a telescope up to it and see it with my own eyes. That's a memory that just doesn't go away.
I think that, so yes, that is one of those things where I went to Griffith and got a tour with him, and we were looking at, we didn't look at Saturn. Did we look at Saturn? I
No,
don't remember what we looked
it was
at.
too windy that night for the telescope to operate.
No,
No,
was
but
that
there was
not
a guy outside with his own telescope.
Yeah,
Oh,
we
okay.
saw. We did. We looked through.
Oh,
We
nice.
looked through a telescope and saw something. It was not awesome, but it worked. It was something.
Yeah, like a star or something.
Anyhow,
Cool story, bro.
Made you feel feelings?
I thought
it,
star.
it did. It made me feel feelings. It wasn't. It was a planet in our.
It made me so emotional right here.
There is something about it. Does
Yeah.
it touches you in a? Okay, I'm not going to complete that sentence, but it is a emotional, almost spiritual experience.
Yes.
There's, Carl Sagan would put much better words to it than I ever could, but
And did.
Yeah. Thanks, Dada. Thanks, floating voice. But we're made of star stuff. We come from out in the stars, and when we go and we look back up at it, there's a certain calling. There's a certain almost like we're trying to go home.
A comfort. With it.
There's a comfort and a sense of wonder and awe and inspiration that comes from all of that, and it's a pretty cool feeling, and it's pretty neat. How neat is that?
It's pretty neat.
Just like the moon. Good. Carrie-Ann's always right. I love that. That's definitely a true thing now. Fantastic.
Actually,
so, did you want to talk about next week and then go to ground support, or do you want to talk about ground support first?
Well, yeah, well, I'll mention that this segment of the show was also made possible by our
Thankfully.
ground support patrons. These are people who've contributed between $1 and $2.49. They will get access to our Hangouts and their name in the show. So thank you to everyone on our ground support team. Once again, we are a crowd-funded show. Every single dollar helps. That's what allows us to do this week after week.
Thank you so much.
No, seriously, from the bottom of
Yes.
our hearts, thank you so much, everyone who's contributed to the show. For more information, head on over to patreon.com/TMRO. For those who don't know, we turn most advertising off on the show because I think advertising is the past, crowdfunding is the future. So we completely and totally rely on your generous support to help make this show go week after week. And it's also what helps bring in Tomorrow's Cities, Tomorrow's Science coming up later this year, and all of the other shows to help get other people excited about human exploration of the cosmos.
And hopefully we're doing that.
Yeah, I hope so. Hope it's working.
I hope you can literally see what your money has gone to.
Next week, we're bringing back another guest, Thomas Cheney. He's going to be talking space law. Had a really interesting article we're going to be talking about. The last time we brought him on, it was one of those, you think, oh, law is going to be boring.
Lawyers.
That sounds so lame.
It sounds lame. It sounds like we're going to be talking politics. I don't want to do this.
So much fun.
It is so incredibly interesting. Things that you never thought you would even conceive of. They're like, oh yeah, I gotta consider this and this and this and all of these other things, and how all of this stuff ties together, and how the world's not black and white. It's a series of steps of gray, right? It's going to be a lot of fun. So that's coming up next week. For all of you watching live, stay tuned. After Dark is up next. So thank you so much for watching. We'll see you guys in a week.